Our universe is a strange and wonderful place. It's filled with black holes, exploding stars, and galaxies hurtling through the vastness of space. To understand these cosmic wonders, we need a new way of thinking, a new set of rules. That's where Albert Einstein's theory of relativity comes in. This revolutionary idea, born from the mind of a single man, reshaped our understanding of space, time, gravity, and the very fabric of the cosmos. Before Einstein, physicists envisioned a universe governed by Sir Isaac Newton's laws. Time was absolute, ticking away at the same rate for everyone, everywhere. Space was a rigid backdrop, a stage upon which the cosmic drama played out. But Einstein, with his bold imagination and relentless curiosity, dared to question these long-held assumptions. He peered beyond the familiar world and glimpsed a universe far more bizarre and beautiful than anyone had ever imagined. Relativity, as Einstein's masterpiece came to be known, is actually two theories intertwined: special relativity and general relativity. Special relativity, published in 1905, unveiled the intimate connection between space and time, forever linking them into a single entity, space-time. General relativity, completed in 1915, extended these ideas to encompass gravity, revealing it not as a force but as the curvature of space-time itself. These groundbreaking theories, though complex in their mathematics, are surprisingly elegant in their simplicity. They paint a picture of a universe where time can slow down, space can stretch and warp, and the fastest thing in the cosmos, light itself, plays a central role in shaping the cosmic landscape. Prepare to embark on a journey into the mind-bending world of relativity, where the universe's deepest secrets are waiting to be revealed. After graduating from the Swiss Federal Polytechnic School in Zurich, Einstein found work as a patent clerk in Bern, Switzerland. It was in this unlikely setting, surrounded by mundane inventions and technical drawings, that his most revolutionary ideas began to take shape. In 1905, Einstein, at the age of 26, published 4 groundbreaking papers that would forever alter the course of physics. One of these papers outlined his special theory of relativity, a radical departure from classical physics. Albert Einstein's work challenged the very foundations of Newtonian physics, which had reigned supreme for centuries. He dared to imagine a universe where time was not absolute but relative, dependent on the observer's motion. It's said that Einstein developed his ideas about relativity by conducting thought experiments. He would imagine himself chasing after a beam of light, pondering what he would observe. These thought experiments, coupled with his deep understanding of mathematics and physics, allowed him to unlock some of the universe's most closely guarded secrets. His work transformed our understanding of the cosmos and paved the way for countless technological advancements, from GPS navigation to nuclear energy. One of the most significant discoveries of this era was the realization that light behaves as both a wave and a particle. This wave-particle duality, as it came to be known, challenged the traditional view of light as simply an electromagnetic wave. It hinted at a deeper, more fundamental nature to light, one that would later be illuminated by Einstein's work, historical physicist. Another crucial piece of the puzzle emerged from experiments with the speed of light. Scientists had long known that light travels incredibly fast, but they assumed its speed was variable, just like the speed of any other object. However, meticulous measurements revealed a startling truth. The speed of light in a vacuum is constant, regardless of the speed of the source emitting the light or the observer measuring it. This discovery, known as the constancy of the speed of light, sent shockwaves through the scientific community. It contradicted the fundamental principles of Newtonian physics, which held that velocities should simply add up. If a train travels at 60 miles per hour and a person on board throws a ball forward at 30 miles per hour, the ball's speed relative to an observer on the ground should be 90 miles per hour, right? Not so with light. No matter how fast the source of light is moving, the light itself always travels at the same constant speed. Historical physicist. This perplexing observation set the stage for Einstein's revolutionary ideas. It was clear that a new framework for understanding the universe was needed, one that could incorporate this bizarre behavior of light. Einstein, with his unique blend of intuition and mathematical prowess, was poised to provide the answer. In 1905, Albert Einstein, a young patent clerk with a head full of revolutionary ideas, published his groundbreaking paper on the special theory of relativity.
Whoa, so this was like a huge deal, right?
Absolutely. This work, a product of his relentless curiosity and his willingness to challenge established scientific dogma, unveiled a universe far stranger and more wondrous than anyone had imagined. At the heart of special relativity lies a deceptively simple yet profound concept. The speed of light in a vacuum is constant for all observers, regardless of their relative motion.
Wait, so you're saying that no matter how fast you're going, the speed of light stays the same?
Exactly. This seemingly innocuous statement has far-reaching consequences, shattering our intuitive understanding of space and time. Imagine two spaceships hurtling through the vast emptiness of space, each traveling at a significant fraction of the speed of light. One spaceship emits a beam of light towards the other. According to classical physics, the speed of the light beam, as observed from the second spaceship, should be the sum of the speed of light and the relative speed between the two spaceships.
But Einstein said that's not what happens, right?
Correct. Einstein's special relativity tells us something quite different. The speed of light remains constant, a universal speed limit that cannot be exceeded. This means that something else has to give, and that something is our perception of space and time. Einstein showed that space and time are not absolute but are relative to the observer's motion. They are interwoven into a single fabric, space-time, that can stretch, warp, and bend.
That's so cool. So how does this work with, clocks and stuff?
To grasp this mind-bending concept, imagine two observers, one standing on a platform and another on a train moving past at a constant speed. Both observers carry synchronized clocks. From the perspective of the observer on the platform, time appears to slow down on the moving train. The clock on the train seems to tick slower than their own. Conversely, the observer on the train sees time slowing down for the observer on the platform. This phenomenon, known as time dilation, is one of the most bizarre predictions of special relativity. It has been experimentally confirmed numerous times, demonstrating that time is not the absolute, unchanging entity we once believed it to be. The implications of Einstein's special relativity extend far beyond the realm of thought experiments. They manifest themselves in a variety of observable phenomena, providing tangible evidence for the theory's validity and fundamentally altering our understanding of the universe.
One such phenomenon is the time dilation experienced by particles traveling at relativistic speeds approaching the speed of light. In particle accelerators, such as the Large Hadron Collider, particles are accelerated to incredible speeds, reaching a significant fraction of the speed of light. As these particles approach relativistic speeds, time dilation becomes increasingly pronounced. Their internal clocks, so to speak, slow down relative to stationary observers. This means that unstable particles, which typically decay within a fraction of a second, can exist for much longer periods when traveling at relativistic speeds.
Another striking example of special relativity in action is the phenomenon of length contraction. Imagine a spaceship traveling at a significant fraction of the speed of light relative to an observer on Earth. From the Earth-based observer's perspective, the spaceship appears to shorten in the direction of its motion. The faster the spaceship travels, the more pronounced the length contraction becomes. This contraction is not an optical illusion, but a real physical effect arising from the nature of space-time itself.
From the perspective of the spaceship's crew, however, everything inside the spaceship appears perfectly normal. They experience no change in length. This discrepancy highlights the relative nature of space and time, emphasizing that measurements of distance and duration are not absolute, but depend on the observer's frame of reference.
These mind-bending effects of time dilation and length contraction, once considered mere theoretical curiosities, have now been experimentally verified countless times, solidifying special relativity's place as one of the cornerstones of modern physics. They demonstrate that our everyday intuition about the nature of space and time breaks down at speeds approaching the speed of light, revealing a universe far stranger and more wondrous than we could have imagined.